Hello DSP guys. This is an extra video. I just want to speak about some hardware problems about filters. The whole syllabus you are thinking about filters from theory part. You didn't take in your lectures what is the hardware problems, what is going on on the DSP kit. I'll speak about 4 points here. The first point in the hardware problems is the number of coefficients. For example, in lab 2, if you remember, we said that we must have at maximum around 100 coefficients. If we open lab 2, we said that the maximum number of coefficients the processor can handle in one interrupt cycle is about 110. So why is that? Actually, if you remember, the DSP was working as follows. The DSP kit is connected with some function generator. So the analog to digital converter is converting a sample, sending it to the DSP, converting another sample, sending to the DSP, converting another sample, sending to the DSP. These samples are convolved with the filter. Okay, if you remember, the convolution is multiplication then addition. If you have a signal of 100 element and a filter of 100 coefficient, you will multiply every element with one of these coefficients. So we have 100 multiplication, then we add all of the outputs. Then on the second time or the next time slot, we shift the signal and continue multiplication as an addition. Shifting the signal, continue multiplication and addition. So it's like the signal is going this way, the filter coefficient is going this way, and we are shifting, multiplying, addition. Shift, multiply, add. The problem here is that we have the number of multiplications equal to the number of coefficients. So if we have 100 coefficient, we have 100 multiplication, 100 addition, which is too much. If the time needed to make one multiplication is 1 nanosecond, which is too small, multiplied by 100, that's 100 nanosecond. And another 100 addition, if we said that it's 0.5 nanosecond, that's another 50 nanoseconds. That's total 150 nanoseconds. Okay, so we have time limitations here. So what we can do, we have either to make the processing faster or to limit the number of coefficients. For example, if I am having a signal every 1 microsecond, so I must make sure that all the processing takes less than 1 microsecond. If I want the processing to take less than 1 microsecond, so I have a constraint on the number of coefficients, which is directly related to the processing. Okay, so why not make the processing faster? Because as we said, the number of processing, the number of multiplication equal to the number of coefficients. The number of addition equal to the number of coefficients minus 1. If you have 100 numbers, then you need 99 addition process, which is too much. So the first practical point on the filters, that we have constraints on the number of coefficients according to the allowed processing time. The more time we have, the more processing we can have, the more coefficients we can have. Okay, so for the first point, the number of coefficients relate to the processing time. In this case, the IR filter is better than FIR filter because IR filter is almost, in most cases, IR filter has much less coefficients than FIR filter. Roughly around 1/8 or 1/10 of the coefficients of FIR filter, which is very nice. Okay, so this point, the IR filter is better because it has lower number of coefficients, so it has lower processing time. FIR filter has much bigger number of coefficients and has higher processing time. The second point is quantization error. What is quantization error? Assumes you have calculated the filter coefficients and one of them was like this. Well, in MATLAB you can write this number, but in digital signal processing on the DSP board you have bits. So to store this number in bits, you need a huge number of bits. It's like you need 70 or 80 bits to store this number. And of course you have limited number of bits. If you have 100 coefficients and every coefficient needs 100 bits, that's too much. That's like you will have 10k bits for one filter only. That's too much. So mostly we don't use all this, we truncate this number, just taking the first 2 or 3 decimals. That's what we call quantization error. So the number we are really using on the DSP are not exactly the same numbers we are using in MATLAB. There is a difference. Well, let's say it is a small difference. It's not a big difference, it's a small difference, but there is a difference. This difference will cause an error, because actually this is not the exact number, so the difference will cause an error. In case of FIR filter, the output depends only on the inputs. So I have inputs multiplied by the coefficients, which are slightly wrong, so the output is slightly wrong. The next inputs are ready for processing, multiplied by the coefficients, which are slightly wrong. The input again is slightly wrong. So FIR filter always have some slight error in the output, but the IR filter is not like this. The IR filter depends on the inputs and the previous outputs. So the first input makes some small error in the output. The second input takes the error from the previous input and adds the new quantization errors. The third input depends on the error in the second input and the error in the first input and the error in the coefficients. The error in the 100 sample depends on the error on the previous 99 outputs plus the inputs plus the error in the coefficients, which means that the IR filter is more likely to have error propagation or error accumulation. The error in the outputs is accumulated in the new outputs, is accumulated, which may cause overflow. Overflow means that the number of bits is not enough to carry the signal, because actually, let's say that there is 0.1, there is a value of 0.1 error propagating. So for the first output it is 0.1, second output 0.2, third output 0.3, 100 output is like 10, 1000 output it's like 100. So there is error accumulation because the coefficients are not exactly the real coefficients, there is quantization error. So in this case, FIR filter doesn't depend on the output, so there is no error accumulation, so it is less dependent on quantization errors than IIR filter. The third point is accuracy. We said that the coefficients are quantized, so there is quantization error. Also, the data which are input are also quantized. If you have data also, it's still like this. You can't make this data input to the DSP. Also the data will need big number of bits, so I can't use this data. I also quantize the data. If the data is quantized, so the data also has quantization error. It depends actually about the hardware you are using. The more sophisticated DSP kit, the more accuracy you have. If you are using some small controllers, maybe Atmel controllers or AVR controllers, it is much less accurate, which may cause processing problems, because now we have quantization errors in the filter coefficients, we have accuracy in data representation, quantization in data, so we have double sources of errors. This may change the performance you hope to. The fourth point, which I called happy news parallel processing, it's something we said here, that the number of coefficients related to processing time. What is processing time? It's the number of multiplication we have, then the number of addition we have. But the multiplications are independent of each other. If you have a signal which contains 100 data and a filter which contains 100 coefficients, when you multiply the first data with the first coefficient, it is independent of the second data with the second coefficient, independent of the 10th data with the 10th coefficients, which means if I have a number of multipliers, I could give every multiplier different data to multiply. So for the first multiplier, I give data 1 coefficient 1. For multiplier 2, data 2 coefficient 2. For multiplier 3, data 3 coefficient 3. So I have 3 multiplications in the same time because this multiplication is independent. So I can use 3 multipliers, 4 multipliers in the same time. So instead of having 100 multiplication taking 100 cycles, multiplication cycles, if I have 4 multipliers, I could make them 25 cycles. So actually the happy news in the filter that it is easily converted to parallel processing. I could make the multiplication process all of them in parallel and then make additions. Since the multiplication process is the heavy computation one compared to the adding, so the processing time can significantly be minimized. Actually, in modern DSP kits, most of them use either 2 multiplications in a cycle. The old one uses 1 multiplication per cycle only. The next ones use 2 multiplications per cycle, which make it twice faster than the old ones. And I think it will continue. I think we'll see versions of 4 multipliers and more in the future. This is something easy that can be implemented. The more multipliers you can have, the faster processing you can have. If you have faster processing, then you can increase the number of coefficients, and all of you, while using the FDA tool design, you have all realized that the number of coefficients, when you increase the number of coefficients, you get better performance. When the number of coefficients is low, you get worse performance. These are some hardware related problems. I just want you to know this. This is not a part of the syllabus. This is just for you. So we have some design parameters. We have in the corner here the number of coefficients, which is related to processing time. And according to these parameters, we consider either IIR or FIR. We have third point, which is quantization error. This is for the coefficients. We have fourth corner here, accuracy of data representation, which is for the data, not for the coefficients. And the fifth point here is the amount of parallel processing we have. So it's kind of multi-design criteria. Depending on the number of parallel processing, the amount of accuracy you want, the amount of quantization error you can handle, the amount of processing time you are allowed to, the number of coefficients you can have, you are now have to choose whether it's IIR filter or FIR filter, or even some designed filter for some special function. Thank you.